So what I'm doing today is column chromatography, very classic demonstration, and I'm going to take Kool-Aid, grape Kool-Aid. And grape Kool-Aid, of course, grapes are always purple, correct? But at least in their coloring scheme, grape Kool-Aid has a purple color to it. So this is just some grape Kool-Aid that I have mixed. I didn't put any sugar in it. And if we look close enough, the color of the Kool-Aid is due to a couple different chemicals. Let's go find them, particularly the red 40 underneath to the right of my finger there, my cuticle, and blue number 1. Those are industry names for the food coloring. All right, they are definitely large advanced molecules like we're studying, and they have the ability to absorb certain wavelengths of light, and therefore they're reflecting or transmitting back the other colors. So what we're going to do is we're going to separate the colors based on chromatography, or at least based on what? Solubility. Chromatography is giving the chemicals a choice. If I'm more polar, I'm going to stay with the more polar phase of the chromatography. If I'm more nonpolar, I'll go with the more nonpolar phase. And that's what we're going to do here. So, but today I'm not using a TLC plate, I'm using a column. And this is called a CPAC right here. And that column is a C18 molecule. It's a hydrocarbon, it's an alkane. As we said before, carbons and hydrogens are have a very similar polarity, so similar we consider them to be non-polar. So if I draw what's in this CPAC here, and it will be a carbon, carbon to carbon, and it keeps going, and we can get 18 of these. And essentially, I fill in the rest with H's, and if this goes on and on and on, that's my molecule. It's a hydrocarbon. And as we said, this bond here between the carbon and H's is essentially nonpolar. Okay? So this molecule has almost zero polar characteristics. Okay? And the solvent we're using is hexanes and ethyl acetate. As we talked about before, that's in our lab, but the solvent I'm using today is isopropyl alcohol. It looks like this. It's 3 carbons, that's your prop, and then we have an OH group at the bottom. So you'd say, okay, isopropyl definitely has some polar characteristics, if I move that down. All right, but also understand that there's some also non-polar characteristics in it as well. As we talk about, things aren't polar or non-polar, they have characteristics of both, okay, as we'll talk about. So that's my solvent. So my stationary phase is that C18 molecules that are in this CPAC, which by the way is nothing more than wax, okay? And this is the liquid alcohol, rubbing alcohol, isopropyl, okay? So let's go ahead and play with this. Let's add some of the Kool-Aid, okay? And here is some Kool-Aid. What color is that? Okay, it's recording, but it's not showing, all right? That color is clearly going to be purple, okay? All right. And now, oh, there it goes. All right, so it's slow, but it's happening. Okay, now, what we're going to do now is take my CPAC and I'm going to flush it out and clean it. So the first thing I'm going to do is I'm going to take it and add some 70% isopropyl, which is the polar phase here. All right, not polar bear, but more polar molecules. I'm going to take the short end of the CPAC. I always put that one to the syringe. That's what we're going to do in our lab today because I want the flow always to be the same way. So I'm going to push this out into a beaker. Okay, push it out. And I'm flushing out the CPAC. So anything that is what? Somewhat polar would be pushed out. Okay? Now, of course, there's some non-polar characteristics to that, okay, as well, so it's not so clear-cut. Now I'm going to flush it out with water, who is even more polar than the isopropyl. Isopropyl has components of both. Water is clearly mostly polar, although it does have some non-polar characteristics, London dispersion forces. However, I'm going to push that out. So I flooded it with the 70% isopropyl alcohol to clean out anything that had any attractions to that. And now I'm going to flood it with the water. And anything that's that crazy polar we pushed out too. Now, my CPAC with the solid is the C18, very, very, very nonpolar. And I've got polar water kind of sitting inside or outside, mixing with the CPAC now. Now, what I'm going to do now is take some of my Kool-Aid, and I could draw some from this point here, but I'm just going to fill it, okay, with a bottle over here. And I take my Kool-Aid. So you can see I just drew some Kool-Aid from another container. Short end of the CPAC goes here. And now I'm going to push the Kool-Aid through a watery background. I mean, there's water in here with this, the C18 molecule. Okay, so the red 40, okay, and the blue number 1, okay, have many, many different characteristics, but they're going to have some non-polar characteristics. They're not going to love water as much as they're going to love the C18. So watch when I push this out. Look at the color of the CPAC and look at the color of the solution coming out. What's happening? What's collecting in the cartridge, the C18 cartridge? The dye. What color is it? Purple. What was the color of the liquid that came out? Right, so I separated the water from this mixture, and the dye preferred the C18 column. Why? Because the dye has stronger non-polar characteristics than it does polar. Even though we say it's water soluble, clearly it preferred the non-polar. Okay, now we're not done yet. I want to separate the red from the blue. As we've learned before, the two molecules we're dealing with here, the red 40 and blue number 1 industry names, they're different molecules. They'll have different solubilities. And a mixture always retains its individual properties. So what I'm going to do is take a 5% solution of isopropyl alcohol. I'm going to take my CPAC off for a second. I'm going to fill the syringe with 5%, at least the best that I can. Fill it with as much as I can. I think it's time for another container. Good enough. Put the short end back in. And now I'm going to push it out over here. And what comes out? The red. The red preferred the 5% solution over the CPAC. Why? The 5% isopropyl solution was what the red dye was soluble in, but the blue remains. In fact, if we weren't colorball like me, you can clearly see that this is now blue, not purple anymore. I don't know if that's clear. If not, I don't know. Blink a few times. Now, I want to separate the blue now. Well, blue has a different solubility, so it's actually soluble in 25% solution, a little stronger. So I'm going to draw up some 25% solution. That's good enough. Short end goes into the, and now I'm going to push out. And that's where the blue comes from. So I was able to separate this dye, or this mixture of red and blue dye based on their solubilities. Now I use column chromatography. Notice something, I separated volumes. I was able to separate volumes of my mixture. That's what we're after today in lab.